On this video on analysis of variance, or Anova, we're going to show you two more examples and then show you what some computer output looks like from a statistical application. The one I'm going to show you here is Stata, but if you get statistical output from other packages like SPSS or SAS, they'll look very similar to this. In the General Social Survey, we're going to look at two different variables that they used there. The first one, our dependent variable, has the mnemonic health. The second one, our independent variable, has the name or mnemonic class. Health is not exactly a continuous variable, but we're going to treat it that way. People were asked, would you say your own health in general is excellent, good, fair, or poor? And were respectively assigned the values of 1, 2, 3, and 4. We're going to take this variable and calculate an average subjective health score. The variable with the mnemonic class asked people to use one of four names to represent their social class. The social classes were lower, working, middle, and upper class. You can see I've broken out the arithmetic averages for health by the different groups, and I've calculated the grand mean. The overall grand mean for the health variable is 2.09. The average score for the lower class people is 2.6. For the working class people is 2.1, for the middle class people is 2.1, and for the upper class is 1.5. Remember that this variable is coded in one direction, meaning that lower scores mean that people feel they're healthier. So we're seeing that the upper class respondents, on average, with a score of 1.5, appear to believe that they're healthier than, for example, the lower class respondents. Here I've put together a spreadsheet, three different spreadsheets actually, for calculating the total sum of squares, the between group sum of squares, and the within group sum of squares. You'll see that I've broken things out by groups, lower, working, middle, and upper. I've got their raw scores. So for example, in the lower group, respondent number 1 responded 3, respondent number 2 responded 2, and so forth. And that I've got the overall or grand mean in the next column, and then finally the difference squared. I did this for each of these groups and then tallied all those sum of squares differences to get the total sum of squares equal to 18.719. In the middle spreadsheet, you can see I'm calculating the sums of squares between. I've broken out each group again, and I have the average health score for each group, 2.625 for the lower class, 2.125 for the working class, and so forth. I also have the overall or grand mean, and we're going to calculate the difference between the group mean and the grand mean and square that difference, and then add those four values up. Here I get a mean square between of 1.698. And then in the lower spreadsheet, I'm going to calculate the within group sum of squares. Remember that this is the variability or variance of people in each group around the mean of that group. So I need the mean of each group, the lower, working, middle, and upper class groups, and I'm going to take for each person in each of those groups the individual score minus the average score for that group squared. I'll add up all those squared differences and I get my mean square within, which is 0.485. Now I have to put these things together into my Anova table to be able to calculate my F statistic. Based on the calculations on the slide before, I'm going to complete my Anova table. The Anova table has a very regular pattern. The rows are always listed as between, within, and total, and we know that our between plus within is equal to the total. I take the three sums of squares from the slide before, and I put them into the appropriate place in the table. My between group sum of squares, 5.094, my within group sum of squares, 13.625, and my total sum of squares, 18.719. I then determine the degrees of freedom for each of those sums of squares. J minus 1 for the between group sum of squares, or 3. N minus j for the within group sum of squares, or 28. And n minus 1 for the total sum of squares, or 31. I take each sum of squares, the between and within, and I divide by their degrees of freedom to get my mean square between and my mean square within. In this case, 1.698 and 0.487 respectively. The ratio of those two mean squares is distributed as an F statistic. So my F calculated is 3.489. I've already gone to the F table in the back of the book and determined that with 3 and 28 degrees of freedom, with alpha 0.05, my critical value or my critical F statistic is 2.95. So when I do my hypothesis test, I compare the F that I calculated, 3.489, to my F critical from the back of the book, 2.95, and in this case, I make the decision to reject the null hypothesis and conclude that at least two of those groups have a statistically significant mean from each other. I've also provided the p-value, which you'll remember is the area under the F distribution that exceeds an F statistic of 3.489 with 3 and 28 degrees of freedom. This tells me that if I wanted to just use alpha 0.05, I could compare my critical value, my alpha value, 0.05, to my p-value, 0.0287. And if my p-value is less than my alpha value, I reject the null hypothesis. And as we talked before in another video, those decisions need to be consistent. You would never reject the null hypothesis using an F statistic and fail to reject using the p-value. You'll always make the same decision. Here's the computer output associated with this particular problem, if I had the raw data and wasn't going to analyze this by hand. At the top of the output, I've just listed out the mean values for each of the groups. I've also provided the standard deviation and number of cases, which I sometimes find useful. The bottom of the output is the Anova Table, and you can see that even though it's generated by Stata or by any statistical application, it looks identical to the ones we've created. The rows are always between and within, and then total sums of squares. You'll get some set of sums of squares, degrees of freedom, your mean squares, and finally you get your F statistic, 3.49. All the computer applications will also give you the p-value, which in this case is 0.0287. Here's our last example. Again, a very small, easy one to calculate, but I decided to show you this one in Stata again so we could make certain that we understand the statistical output. In this example, we've got a set of housing prices for houses that are located in areas that have low pollution, moderate pollution, or high pollution. And we're asking the question, is the average price of housing equal to each other depending upon the level of pollution? That is, are houses that are sold in high pollution areas roughly the same price as those in low pollution areas? Again, when we look at the statistical output at the bottom, I like to provide the means of the three groups. The average price of housing in low pollution areas is $81,200. The average cost of housing in the moderate pollution areas is $77,000, and in the high pollution areas, $55,400. Clearly, there are differences in these averages, but the question we're asking is, are the differences statistically significant? Below that's our Anova table. We really don't have to spend a lot of time now that we understand the logic of Anova, thinking about all these different groups and doing all the calculations. We can go straight to either the F statistic, the 1.92, or the p-value, 0.1887. In this particular example, regardless of the alpha value we might have used, 0.05, 0.01, or 0.001, we would fail to reject the null hypothesis of no difference. Despite the fact that these averages seem to be quite different from each other, there is not enough statistical evidence here to reject chance, or the notion that these three are different because of sampling error. Now, why would such large differences not be statistically significant? My guess in this particular case, because the numbers are really in the right direction. We actually expect a priori that the average value of housing in high pollution areas is lower than in low pollution areas, is that we have a very small sample size. And as you remember from the whole set of lectures on sampling distributions, that one of the things that really affects our standard error and our test of significance is sample size. We tend to make better and more precise estimates with larger samples. In this particular example, we have such a small set of houses that even though there are big differences in the averages across them, it's probably due to a large standard error due to a very small sample size. Now, that doesn't mean I can reject the null hypothesis, but it does lead me to believe that if I were to collect more data, and if the averages stayed in the same, if the differences remained, that I would probably find them to be statistically significant. I hope this video helped you understand how to read the computer output and where these numbers come from, and also the value of using a spreadsheet to calculate these things when you have large problems. As always, if you have any questions, please let us know, and we'll see everybody in class.